Okay, back in chapter 3 we had our mean value theorem, or the MVT, and that dealt with derivatives and slope. There is also a mean value theorem for integrals. So a couple sections ago we saw that the area of a region under a curve is greater than the area of the inscribed rectangles and less than the area of the circumscribed rectangles. The mean value theorem for integrals states that somewhere between those inscribed and circumscribed rectangles there is a rectangle, a single rectangle, whose area is precisely equal to the area of the region under the curve. And I think this is easiest seen graphically. So here in the photo we have our curve f of x, and we have the area under that curve. And we also have this rectangle, and the area that is within this rectangle is exactly equal to the area under the curve. Because here there's some area that's under the curve but above the rectangle, and here's some area that is in the rectangle but above the curve. And these two areas sort of wash each other out. And again, what we have is a rectangle with the same amount of area underneath the curve. And there is some point C. Here's our interval from A to B. There exists some point C in that interval that when we go up to the curve and then over to the y-axis, that height, f of C, is the height of the rectangle, and the distance between A and B is the length of that rectangle. The area of that rectangle is again the area that's precisely under the curve. So in the box we have theorem 410, the MVT for integrals. If f is a continuous function on the closed interval from A to B, then there exists a number c somewhere in that closed interval such that here's our definite integral of the function, that's the area under the curve, that is exactly equal to f of c, again that's the height of the rectangle here, times b minus a, or the length of that rectangle. And note down here, note that theorem 410 does not specifically tell you how to determine what point C is. It merely guarantees the existence of at least one number c in that interval that holds this property. And this leads us to the average value of a function. The value of f of c, given in the mean value theorem for integrals, is called the average value of f on that interval from A to B. So our definition for the average value of a function on an interval: if f is an integrable function on a closed interval A to B, then the average value of the function on that interval is, and here is just our definite integral from A to B of our function f of x dx. What's different out here is the fraction in front of the integral sign, 1 over b minus a. That's just a fraction, 1 over upper limit b minus lower limit a. That gives us the average value of the function. So here in example 4, we're going to find the average value of a function. Find the average value of f of x, which is 3x squared minus 2x, on the interval from 1 to 4. So I'm just going to copy down that notation from the last slide, 1 over b minus a. And then we want our definite integral from A to B of f of x dx. So let's put this information that we were given into this format. So our integral is going to be from 1 to 4. That is our interval, 1 to 4. And that also tells us that our fraction out front is going to be 1 over b minus a, or 4 minus 1. Our function is 3x squared minus 2x and dx. So let's see, our fraction out front is going to be 1/3. And then here let's take the antiderivative. We're going to have 3x to the third divided by 3, so the 3's will cancel out. We're left with x to the third. Minus, raise the power by 1, that would be 2x squared divided by 2. Again, the 2's will cancel out, so we're left with just x squared. And then we have our bracket on the other side from 1 to 4. So we're going to evaluate that definite integral. Our 1/3 is out front. That will be distributed across everything. So I'll go to red for my upper limit. We're going to plug that 4 in where we see an x. So we're going to have first is going to be 4 to the third minus 4 squared. And then we minus running our lower limit through. So we're going to plug the 1 through there and get 1 to the third minus 1 squared. And again, that 1/3 is distributed across all of it. So 1/3. In the first set of brackets, we're going to have 64 minus 16. So this is 64 minus 16, which is 48. And then minus, put that in its own parentheses, minus 1 to the third is 1, minus 1 squared is 1. So we're going to get minus 0. And we're just left with 1/3 of 48, which is equal to 16. And if we go back to the picture here, again, this is our average value. Our f of c is about 16. That's just the height of the rectangle, and the width is 4 minus 1, or 3. So a 3 by 16 has a area of 48. There are 48 square units in this rectangle, and that tells us there are also 48 square units underneath the curve. And that's what we found here was 48 before we did the 1/3. Remember, that was 1 over b minus a, and that gave us the average value across that interval. Now here's example 5. This isn't in your notes, but it is in the book. It's pretty complicated, and it shows a good real-life application of these integrals. So at different altitudes in the Earth's atmosphere, sound travels at different speeds. At thicker atmospheres, sound goes slower. Higher at thinner atmosphere, at higher atmospheres, thinner atmospheres, it travels faster. So the speed of sound, s of x in meters per second, is modeled by this piecewise function. So let's see here. Our altitude is in kilometers. So if you're between 0 and 11.5 kilometers, the speed of sound is modeled by the function negative 4x plus 341. If you're between 11.5 and 22 kilometers of altitude, the speed of sound is 295. Between 22 clicks and 32 clicks is 3/4 x plus 278.5, and so on up to 80 kilometers of height. So where x is the altitude in kilometers, what is the average speed over this interval? From 0 to 80 kilometers, what's the average speed of sound? So here we have to integrate piece by piece. So we break the integral into 5 parts right here. From 0 to 11.5, 11.5 to 22. These are our different intervals. So we have our first integral from 0 to 11.5 of this function. Well, we integrate, find the definite integral, 3,657. Our next piece is from 11.5 to 22 kilometers. We integrate the function, which there is no function there, it's just 295. We get our value. From 22 to 32 kilometers, we integrate this function, take the definite integral, and get this value, 2,987.5. And we continue through the piecewise function until we get values for all of those definite integrals. And we add the values of those 5 integrals, and we get the value from 0 to 80 of s of x dx is 24,640. And remember, to find the average, we need our fraction out front. 1 over b minus a becomes 1 over 80. So we take the value we found above here, divide by 80, and get the average value for the speed of sound between 0 and 80 kilometers of altitude is about 308 meters per second. And here's a little graph of the speed of sound on altitude. Okay, now let's talk the second fundamental theorem of calculus. Earlier you saw the definite integral of function f on the interval from a to b was defined using the constant b as the upper limit of integration and x as the variable of integration. So here upper limit was b, and that was usually just a constant, and x was our constant, or our variable of integration. However, a slightly different situation may arise in which the variable x is used for the upper limit of integration. Instead of a constant up here, it might be a variable like x. To avoid confusion in using x in two different ways, t is going to be temporarily used as our variable of integration. And here's a key idea. Remember that the definite integral is not a function of its variable of integration. The integral is not determined by this variable down here, f of t. It's more determined by our upper limit, and here it is a variable. So on the left, the definite integral as a number from a to b of our function. The definite integral as a function of x. You know, we have our lower limit a, our upper limit is a variable, and then we also have our variable of integration. The definite integral is not a function of this variable of integration. So, example 6. Evaluate the function f of x from 0 to x of cos of t dt. We could do 1, 2, 3, 4, 5 different problems. We could do the integral from 0 to 0 of cos of t dt. And then we could do the definite integral from 0 to pi over 6 cos of t dt. And then the definite integral from 0 to pi over 4 cos of t dt. We could do that separately for each, or we could just come up with a new function, and we could just plug those values in directly. Oops. So let's just evaluate this integral like we have been doing with the upper and lower limits that we have. So we have the definite integral from 0 to x of cos of t dt. Well, let's take the antiderivative. What do we derive to get cosine? That's sine. Sine of t. And then we're going from 0 to x. So we plug in the upper limit x, and we get sine of x. Minus, we plug in the lower limit 0. That kind of looks like a 6, but trust me, it's a 0. We plug in the 0, minus sine of 0. Well, what is sine of 0? On our unit circle, we'd be right here at an angle 0. The sine value, again, is our y-coordinate. So there, the sine of 0 is 0. So we get sine of x minus 0, or just sine x. So now we use f of x equals sine x. So we can just start plugging in these given x values. And let me clear a little space here. So we plug in our first x value, 0. F of 0 is just sine of 0, and we just said that value is 0. We can plug in pi over 6. F of pi over 6 equals the sine of 1/6 pi, and that's equal to a half. And then we can check a quarter pi. F of a quarter pi equals sine of a quarter pi, and that's equal to square root of 2 over 2. And then we could do the same thing for pi over 3. F of a third pi equals sine of pi over 3, and that's equal to square root of 3 over 2. And we could check half pi. F of a half pi equals sine of a half pi, and that's equal to 1. So there's our inputs and our outputs, our values. And let me bring up the graph here. So we can, using f of x as sine x, we got the following results. F of 0 equals 0. There's no area under the curve. Our upper and lower limits were the same. When we got out here to pi over 6, the area under the curve was a half. We went out a little farther to a quarter pi. The area under the graph increased to square root of 2 over 2. Then we were out to a third pi. The area under the curve was root 3 over 2. And we got all the way out to half pi, and that's where we hit the x-axis. The area under the curve was 1. So you can think of the function f of x as accumulating the area under the curve. Again, here is sort of that we were rolling out across the x-axis. As we rolled out farther and farther, we accumulated area underneath the curve. So we can think of this as an accumulating area under the curve from f of t equals cos t, from t is 0 to t equals x, whatever x value we choose. For x is 0, the area is 0. For x equals a half pi, the area is 1. This gives the accumulated area under the curve, the cosine curve, on the entire interval from 0 to a half pi. This interpretation of an integral as an accumulation function is often used in applications of integration. In example 6, note that the derivative of f is the original integrand with only the variable changed. That is, d dx, the derivative of our function f of x, which was derivative of sine x, or the derivative with respect to x of our integral from 0 to x cos of t dt, it's almost like the derivative and integral, they're inverse functions, so they canceled each other out. The x just dropped down into the function and took the place of t and became cos of x. This result is generalized in the following theorem, the second fundamental theorem of calculus. So if f is a continuous function on an open interval I containing a, then for every x value in the interval, the derivative with respect to x of our integral from a to x of f of t dt is simply f of x. Again, it's almost like the derivative and integral cancel each other out. The upper limit x drops down into the function, and we just get f of x. And that's sort of what happened back here. Our x value just dropped down in here, and it became cos of x. So here in example 7, this is a very straightforward use of the second fundamental theorem of calculus. We're taking the derivative with respect to x on the definite integral from 0 to x of the square root of t squared plus 1 dt. Again, this is very straightforward. The derivative and integral will cancel out. We're simply using our upper limit x, that's going to drop down into this function, and this will become the square root of x squared plus 1. And there you have it. In the next example here, example 8, using the second fundamental theorem of calculus, find the derivative of this. F of x equals the definite integral from a half pi to x to the third cos of t dt. Now that's the difference here. In the last example, or in the theorem, it was our upper limit was simply an x. Now it is x to the third. So this is sort of a chain rule application here. So we got to be thinking chain rule. When we did chain rule, we thought about our inner function as u. We let u equal the inner function, and then we had the derivative of that, du. So here our u value is going to be x to the third. And now let's work with the notation. We want to find the derivative of capital F of x. So we're looking for f prime of x. And that's equal to df du times du dx. And that notation should look familiar. That is chain rule. So another way we can rewrite this first term, df du, is d du of f of x. And that's going to be times our du dx. Well, let's see here. This f of x is f of x. So we can substitute this definite integral in place of f of x. So what we're going to have is d du of our definite integral from a half pi. And let's do our u substitution right now for the upper limit. The upper limit was from a half pi to x to the third. Now our x to the third has been replaced with a u. And that's our function is cos of t dt. So we made our substitution for f of x, and we still have our times du dx. So when we apply this second fundamental theorem of calculus, the derivative and integral sign will cancel each other out. This u will drop down into our function, so we're going to have the cosine of u, and the dt is consumed also in the process, times what is du dx. Well, here's our u value. If we derive both sides with respect to x, we're going to get 3x squared times 3x squared. And we can, substitute x to the third back in for this u. So we have cos of x to the third, and then times 3x squared. There we go. Are we sure that our answer is right? Can we check it? Of course we can. Let me get this out of the way. And I'm going to put this up in the corner. Oops. So here was our answer. Is that correct? Let's verify. And that we're just going to integrate what we started with, as we always have. So the definite integral from a half pi to x to the third of cos of t dt. So, the definite integral, what is the antiderivative of cosine? Of course, that's sine. The sine of t from a half pi to x to the third. So, plug in the upper limit. We are going to have sine of x to the third minus, plug in the lower limit, half pi, sine of a half pi. And what is the sine of a half pi? 1. So we're going to have the sine of x to the third minus 1. Okay, what happens when we derive this? Let's take the derivative, d dx, of this function we just found. Sine of x to the third minus 1. Okay, what's the derivative of sine? Derivative of sine is cosine of the same quantity, x to the third, times, by the chain rule, our inner function is x to the third. The derivative of that is 3x squared. And lo and behold, we got the same thing. We've just verified our answer. Okay, well, that's going to end this video here. I am going to come back where there's going to be a part 3 to this, where we do a particle in motion problem. That shows up quite often on the AP test for a free response question.